Hi everyone, today we're going to be continuing our discussion of the different groups of the periodic table by looking at the transition metals. So we've got a couple goals here. First, we want to learn the properties of the transition metals, and we're going to add them to our periodic table. So we're going to be shading that in, which means you'll need a colored pencil. We want to understand the difference between a conductor and an insulator, and we want to understand a new type of bond called metallic bonds. So far you've talked about ionic bonds. Now we're going to add metallic bonds to our toolkit. And we're going to learn how this makes metals particularly conductive. So before we get started, make sure you have your periodic table, make sure you've got a colored pencil, and that you have note paper and pencil to take notes with. So the first thing I want you to do is have you fill in these elements on your periodic table. So you're going to be filling in elements 21 through 30, 39 through 48, 72 through 80, and 104 through 112. This block of elements has a couple names. They're called the transition metals, so you can see that I've added transition metals to my key down here. They're also sometimes known as the B block. So the A block includes these two on the left and these 6 columns on the right. The B block is this big center section. And the thing about the B block elements is they're just a little bit more complicated than the A block elements. So a lot of the sort of shortcuts and tricks that we've learned that work really well for things in the A blocks actually won't work for the transition metals. So go ahead, take a moment, pause this video, fill in those elements on your periodic table, and when you're done filling them in, you can hit unpause. You ready? All right, let's proceed. So normally, right after I have you fill in those elements on the periodic table, we start talking about what kind of charge atoms in that group have if they form ions. I said before that the transition metals were a little bit more complicated than the A groups. So for those A groups, groups 1A, 2A, that's like hydrogen's column, beryllium's column, and the 6 columns on the right-hand side of the periodic table, for those A groups, you can use something called the octet rule, which is you can say everything is trying to either empty out their electrons or get up to 8 electrons. And this works beautifully for things in the A block. The problem is that's not actually how it works. It's just a convenient shortcut. In reality, electrons are not gathered in these beautiful, neat little electrons. They're not in these pairs in the north, east, south, and west quadrant like we've been drawing them with our Bohr-Rutherford models. Those are models, and models are not the same thing as the actual atoms. In reality, atoms are much more complex. And it turns out that that Bohr-Rutherford model is really, really good for predicting the properties of things in the A group, which makes it useful. But when it comes to the transition metals, it just doesn't work well enough. It doesn't capture enough of reality to explain how these things work. So the way that the electrons in the transition metals are arranged is a lot more complicated. There's a whole different type of orbital that we start seeing in the transition metals. And because of this, there are actually multiple ways for the atoms in the transition metals to gain, or not really, to lose electrons. They do lose electrons like all metals. They tend to form positively charged cations. But there's often more than one way that they could lose electrons and become stable. There's more than one path to becoming stable for them. And as a result, many of the transition metals can form multiple ions. So for example, if you have a sodium cation, sodium is in column 1A, every single sodium cation will have a charge of +1, always. But if you have something like an iron cation, iron is element number 26, it's in the transition metals, iron could form ions with a charge of +2, or it could form ions with a charge of +3. Copper, which is element number 29, another transition metal, could form ions with a charge of +1, or sometimes it forms ions with a charge of +2. So with these transition metals, you can't necessarily predict as easily what the charge of ions will be, at least not without learning a lot more chemistry. So the good news is, in high school, you will learn how to predict what kind of charges these elements can have. But for middle school, if I need you to know what kind of charge a transition metal has, I will tell you what their charges are. So you're never going to have to predict the charges of a transition metal. But you do need to know that, like all metals, they always form cations. So, it is right there in the name. Transition metals are metals, and that means they have all of the metal properties. So just like our alkali metals, just like our alkaline earth metals, these have the metal properties. They are malleable, which means you can hammer them into different shapes without them breaking. They are ductile. You can use them to make wires. They are conductive, which means they conduct both heat and electricity. And they always form cations. So if you look at what is in those transition metals, you might notice certain elements like copper. There's a reason why we used copper tape as our conductive material when we did paper circuits. Copper is extremely conductive, like many of the transition metals and like metals in general. So all these transition metals have that lovely property of being conductive. Now, not every element is conductive. Oftentimes you'll have nonmetals, and those nonmetals will frequently be what's called insulators. So for example, you're generally not going to conduct electricity well just straight through air, right? I can't have a battery on one spot and just hold an LED somewhere else and expect the electrons to make it from the battery through the nitrogen gas in the air into the LED and back. That's not going to work. If I want to make a circuit, I really want to make it out of something metallic. But we have things which are conductive, like our metals, and we've got things which are not conductive, which is oftentimes our nonmetals, and those things are called insulators. So transition metals, like all metals, are conductive, and oftentimes transition metals will be particularly conductive, so they're really good at it. In fact, transition metals are kind of the most metal-y of metals. They're the ones that are the most malleable. They have the best conductors. They oftentimes have really high melting points, so you have to get them very hot in order to turn them into a liquid, and ridiculously hot, like hearts of stars hot, to get it to turn into a gas. So the transition metals are sort of the most stereotypical metals you could have. Now, I've talked a lot about how transition metals are conductive. So if we're talking about how conductive transition metals are, and metals in general, we need to understand why. And the reason why metals are conductive is because if you have metals, there is a special type of chemical bond that only metals can do, and this is called a metallic bond. So one thing I want to be really clear about with bonds is bonds are all about what the valence electrons are doing. So we've talked about ionic bonds already, and in ionic bonds, you either gain or lose valence electrons in order to form an ion, and then ions with different charges can be attracted to each other like magnets. Metallic bonds also has to do with what the valence electrons are doing. So you're used to thinking about valence electrons as belonging to a specific atom. So if we have, say, a sodium atom, it has 11 electrons total and exactly one valence electron, unless it becomes an ion, in which case it loses that one valence electron and then it doesn't have any. Metals can do this really special thing called metallic bonds. And metallic bonds are when all of the electrons in a hunk of atoms, so if you have a piece of iron, there are billions upon billions of atoms there. And the valence electrons just sort of drift freely from one atom to the next. So if you add in extra electrons at one place, they can just be shared from that atom to the next one, to the next one, and so on. So we can keep just moving electrons freely between atoms in a metallic bond. It's as though the valence electrons don't really belong to any one atom. Instead, they're just sort of shared freely amongst everyone. So metallic bonds are sort of the communists of atoms. Every electron belongs to everyone communally instead of belonging specifically to one atom. So, metallic bonds are when valence electrons are freely shared amongst all of the atoms that you have present. So here's a picture. Imagine each of these is a metal atom. These electrons don't really belong to any one atom. Instead, they can move freely. And that means that if we add an extra electron over here, maybe from a battery, then this atom will be like, oh, I have an extra electron. Here, let me just pass that off to the next atom. And then the next atom in the line will be like, oh, extra electrons, this is more than I need. And they'll pass one of their electrons on to the next one. And so as you go, electrons can just be passed freely throughout the metal. And that's why something like our copper tape when we were doing paper circuits was so conductive. If we gave extra electrons to copper at one end of the tape, it would just pass that off to its neighbor, and they keep passing those electrons down the line until they find their way to something that needs those electrons, namely the other side of the battery. So metallic bonds are why metals are so conductive. Now, the other thing that's important to note about metallic bonds is because these atoms are sharing the electrons freely, you can actually have metals be totally stable just by themselves. You can store a hunk of iron in a warehouse and still have iron a few minutes later. This is very different from most other elements. If you take something like a non-metal, like say fluorine, one of our halogens, you're not going to have a single fluorine atom in nature. Instead, they tend to pair up in order to become stable because they can't be stable alone. Metals, you could just have a whole bunch of sodium and you'd have individual sodium atoms and it would be fine. You could have a hunk of iron, you could have a hunk of gold. And that's why in chemical reactions, oftentimes you'll see a metal by itself, not part of a molecule. And that's perfectly fine. It's a stable way to be. So one of the nice things about these metallic bonds, there's two main things that it lets you do. One, it lets you be stable with just metal without needing to have it bond to anything. And two, metallic bonds are what makes metals so conductive. And that's it for today's lesson on the transition metals. So at the end of this, you should have a periodic table with the transition metals colored in. You should have in your notes what the difference between a conductor and an insulator is. So remember, conductors can conduct heat. Insulators don't conduct heat or electricity well. And you should have the properties of the transition metals written down. So transition metals, same properties as all metals, but they also have a few important properties like the ability to form multiple different ions. So iron, for example, forming +2 ions or +3 ions.